Newton's third law states that for every action, there is an equal and opposite reaction. So this happens when two bodies or two objects are in contact with each other. If a body A exerts a force on body B, then body B will exert a force on body A that is equal in size magnitude and will act in the opposite direction. This therefore results in the two objects not going through each other because of the equal and opposite reaction force. So we will use Newton's third law in this question. The question reads, a light scale pan is attached to a vertical light and extensible string. And the scale pan carries two masses, A and B, as we can see in the diagram. And the mass of A is 400 grams and the mass of B is 600 grams. A rests on top of B as shown in the diagram. And the pan is raised vertically upwards using the string with acceleration of 0.5 meters per second squared. Now, when tackling a question like this, where two objects are in contact with each other and we are interested in the force exerted by one on the other, which is what the question goes on to say, force exerted on mass B by mass A, force exerted on mass B by the scale pan. So when we're interested in the contact forces, these reaction forces between the objects, what we need to do is find another way of drawing this diagram such that we can see all the forces between each object. So how I tend to do this is redraw the diagram, but with the objects separated, kind of floating. So here's object A, and then I'll draw object B. And object A has a mass of 400 g, so its weight is 400 g acting downwards. Object B has a mass of 600 grams. Oh, sorry. 0.4 g, because mass is in grams, so turn it into kilograms. 600 grams is the mass of object B, therefore its weight is 0.6, which is kilograms times g. I'll draw the scale pan here, again spaced out. I've got the string, so there's tension in the string. I'll label that as T. The scale pan itself is light, as mentioned in this question, which means it has no mass, so no weight there. Now, because there is contact between the scale pan and the object B, there is a reaction force there. So what object B feels, it feels something pushing up on it, a reaction from the scale pan, and likewise the scale pan experiences something pushing down on it, which is the reaction from object B. So a common misconception is that this reaction here is the weight of object B. It's not. The reaction force, the weight is transferred through this reaction force. So we would never write down that the weight is felt by the other object. Instead, we think about it as reaction forces. So I will indicate this as reaction 1, R1, and I will, Newton's third law states that if those two object B and the scale pan, are in contact with each other, they're not going through each other, then there must be an equal and opposite reaction force. So there will be an R1 there as well in the opposite direction. Now we have another contact between object A and object B. And again, I will draw the reaction forces between these two objects here as well. So object A will feel object B pushing up on it. And object B will feel object A pushing down on it. These two forces will be equal and in opposite directions, so I will label this as R2. So that's the reason why I spaced these objects out and not draw them on top of each other as shown here, but instead space them out so then we can actually draw the forces experienced by each object separately, and each arrow that we've got there which touches an object indicates the object. It indicates the forces on that object. So now we're in a position to go and apply Newton's second law to solve the question. So let's go and take a look at applying Newton's second law, and we will try and look at what happens in part A. So part A is asking us to find the tension in the string. Now, to find the tension in the string, I can start by first of all looking at the whole object. I can look at the whole system, so that will be the scale pan plus the A and plus the B, or I can start looking at each individual objects as well, A or B. Now we know that this scale pan is accelerating vertically, and the acceleration is 0.5 meters per second squared. And it says it's raised, so I will indicate that acceleration here, 0.5 meters per second squared. Okay, so if I just consider F equals ma on the scale pan, take up as positive, and I'll just make a note, this is the scale pan. Then I will only look at the forces felt by the scale pan. So there is a T on the scale pan, and we can see that there is a R1 felt by the scale pan. They're the only arrows which are on the scale pan, so they'll be the only forces felt by the scale pan. So what do we have here? T minus R1 is equal to the mass of the scale pan, which we know is 0, times the acceleration, which is 0.5. Now this gives us T is equal to R1. It doesn't give us any information here, so can't really solve this at this stage. We need to go and find some other. Equation. So then we'll consider then. Let's take a look at just considering. So we will consider here just particle A then. So if we look at particle A alone, we can then say, again, do F equals ma on particle A. And again, up as positive. And if we apply that, then we can see that the forces experienced on particle A is R2 there, and this 0.4 G. So what do we have? We have R2 acting upwards minus 0.4 G is equal to the mass of that object, which is 0.4 kilograms, times the acceleration, which you know to be 0.5. Again, here we have got R2 as an unknown. So we need to find out what R2 is here. So let's go and rearrange and find out what R2 is. R2 is equal to 0.4 times 0.5 plus 0.4 G. Okay. And if we find out what that is, that gives us 4.12 newtons is what R2 is. Now, we found out what R2 is, but the question is not asking for R2, it's asking for tension here for part A. So let's go and consider now F equals ma on particle B alone. So if we consider F equals ma on particle B alone, what are the forces that are felt by particle B? Well, there's an R2 here, there's an R1 here, and there's a 0.6 G here. So let's go and apply this to our Newton's second law, F equals ma. Forces acting upwards, we have R1 minus R2 minus 0.6 G is equal to the mass of particle B, which is 0.6 kilograms, times the acceleration, which is 0.5. Now we already know what R2 is, so we can substitute that in here to work out what R1 is. So R1 is equal to 0.6 lots of 0.5 plus 0.6 g plus R2, which we know to be 4.12. This then gets us 10.3 newtons. So we've worked out what R1 is. Now remember, right at the beginning, we wrote down that T is equal to R1 by using F equals ma on the scale pan. So then we can go and say T is equal to R1, so T is also equal to 10.3 newtons. So we found out what the tension is. Now, part B of the question goes on to say, find the force exerted on the mass B by the mass A. So the force exerted on mass B by mass A. Well, what is that force? Let's go and consider that. So the force exerted on mass B by mass A is reaction 2 that we have here. Okay, R2. So part B is asking for what this reaction 2 is. We've already worked this out, so I'll just go and write down here part B, R2 is equal to 4.12 newtons. That's what it was asking for. And we're also asked for the force exerted on mass B by the scale pan. So that's referring to reaction 1. So here we're after reaction 1, the force exerted on mass B by the scale pan. Reaction 1 we've also worked out, it's 10.13. So let's go and write that down. You'll find often that when you're doing the working out, that you work out certain parts before the other parts. That's fine. Once you get those answers and it's asked for those answers later, just write those answers down. You've done the working out. You do not need to repeat the working out again.